Hello, today we're going to be talking about electromagnetic radiation and how that interacts with electrons in atoms. So in order to begin this chapter, we have to realize that you should have already watched the video on the electromagnetic spectrum, talking about the details of all the different regions, so I won't spend much time in this discussion on that because I'm expecting you have already watched that video. We're going to be looking at wavelengths a little bit and how that relates to energy and how frequency relates to energy with respect to electromagnetic radiation and how that relates to electron transitions in atoms. So we'll be looking at, first of all, some simple calculations with the Bohr model, and then we'll be looking at some more complex concepts with quantum mechanics. However, you will not have to do any of the calculations for the quantum mechanics. You just need to understand some of the quantum numbers and how that relates to energy levels and electron configurations later on in this chapter. So that's what's coming up here. Now, first of all, let's consider some basic properties of waves. If we consider how long a wavelength is for electromagnetic radiation, or in fact how long a wavelength is for any wave, if we go from the top of a peak to the next adjacent peak, that would be a wavelength, or from the bottom of a trough to the next adjacent trough with respect to our wave, that would be how long our wavelength is. The height from the midpoint of the wave to the top of a peak or the bottom of a trough would be considered our amplitude for the wave. Now, when we start working with wavelength in this chapter, we're going to be using the Greek letter lambda to indicate the wavelength. So that looks a little bit like an upside down Y here. That's this wavelength we've designated as from a peak to a peak or a trough to a trough. And as I said, the amplitude is from the midline of the wave, the midpoint, to either the top of a peak or the bottom of a trough. So we might use some of those terms. We'll be using the Greek letter lambda for wavelength to represent wavelength in our calculations. Now, if we consider looking at, let's say, light, if we look at light, the higher amplitude light we see of the same wavelength would be brighter. If we have the same wavelength but we have a lower amplitude, that would be dimmer. This will relate to constructive interference. If we have more light with that same wavelength, the intensity of the light, the amplitude of the light would increase. It would become brighter as we have more of that light coming through. But every single portion of that light has the same wavelength. If we're talking about the brighter or dimmer light of that same wavelength, the amplitude just changes. Now, if we want to consider the frequency of a wave, well, a frequency of a wave, we're going to use the Greek letter nu for frequency. If we were to consider, let's say, a seagull sitting on water and we were looking at water waves, every time one of the peaks of our water waves passed underneath that seagull, every time we repeated that peak passing underneath, a full wavelength passing underneath that seagull, we would relate that to being basically the number of cycles that are occurring with respect to this wave passing through a point in space. And so the more frequently we see a wavelength pass under that point in space or pass under the seagull here, we could talk about the frequency of the wave increasing. Now, we usually consider this as being the cycles of the wave passing through that point in space for every second in time, but we use a unit called hertz. So hertz is equal to 1 cycle per second, and it's the unit we will use for frequency. So realize hertz is also related to inverse seconds, which we'll use to cancel units on some of our calculations. Now, the speed of any wave would be equal to basically the wavelength of the wave times its frequency. So if I had water waves, I'm talking about the speed of a water wave, I can take the wavelength times the frequency to get that speed. However, if I'm dealing with electromagnetic radiation, we're going to define the unit for speed as a C for my unit for my electromagnetic radiation, and the speed of electromagnetic radiation in a vacuum, I would like you to memorize, is 3.00 to 3 significant figures, is as far as I'm asking you for this course to memorize, times 10 to the 8th meters per second. Okay, so that's going to be the speed of electromagnetic radiation in a vacuum, no matter what form of electromagnetic radiation we have, no matter its wavelength, no matter its frequency. So I can say the speed of that electromagnetic radiation, C, is equal to its wavelength lambda times its frequency nu. Okay, so that's an equation we're going to be using here quite a bit in this chapter. So we can relate to considering visible light as well as other portions of the electromagnetic radiation being electromagnetic waves. We can credit that to Maxwell in 1873. I'm not going to spend much time on the history behind that, though our more advanced courses do. First of all, I want you to realize that the electromagnetic radiation can relate to the emission and transmission of energy in the form of electromagnetic waves. They can pass through a vacuum, or they can interact with matter, as we'll be seeing in this chapter. So if we can look at the speed of light in a vacuum, as I said, that we're going to use the symbol C for the speed of light in a vacuum, and I would like you to memorize it's 3.00 times 10 to the 8th meters per second. This speed of light is the same no matter what type of electromagnetic radiation we're looking at. It doesn't matter whether we're looking at visible light, gamma rays, X-rays, UV, IR, any of the different electromagnetic regions of the spectrum. We will talk about the same speed in a vacuum. They all have the same speed of 3.00 times 10 to the 8th meters per second. So I do ask that you memorize that one. It may not be given on the test. Okay, so if I consider the speed of any wave, as I said on the previous slide, is equal to its wavelength times its frequency. So we can use the following equation. The speed of light, or the speed of electromagnetic radiation, is equal to its frequency times its wavelength. So if I have any one of these variables unknown, I can solve for the other. So for example, if I knew the wavelength but wanted to solve for frequency, we could go ahead and divide both sides of this equation by the frequency. And we would generate a new equation that the wavelength of light is equal to my speed of light divided by frequency. If I wanted to solve for frequency, I could go ahead and say, well, then frequency would be equal to the speed of light divided by wavelength. Now, you may be expected to use any one of these three equations, so I would recommend that you memorize them. Usually I tell students just to memorize that the speed of light is equal to my wavelength times my frequency, and just with their algebra be able to solve for the unknown variable, be able to solve for either frequency or wavelength when given wavelength or frequency. Now, I want to remind you, remember that the units for my frequency are hertz, and so those are going to be for frequency. Hertz is the same as cycles per second, so 1/seconds that we're looking at there. And remember that my units for the speed of light is meters per second if we're considering those units, so that's meters per second. So you can see the seconds would cancel here, but I want to note that we can see from the speed of light constant we're using that we have units of meters per second. So my wavelength when I'm doing these calculations must be in meters. So if I were given a wavelength in, let's say, nanometers or any other prefix for the metric system, I might have to convert to meters first before I use this equation. So just be aware of that. Those are the units we're working with here. Now, as I said before, you should have watched the video on the regions of the electromagnetic spectrum, so I'm not going to spend much time on this slide discussing that, but I do want to relate energy to my different frequencies and wavelengths. I want you to notice that as wavelength becomes smaller, we have higher energy. So here's wavelength in nanometers. If I was going to use it in my calculation of to find wavelength, the speed of light divided by frequency would be equal to a wavelength in meters. If I wanted to relate it to nanometers, I'd have to convert from meters to nanometers to relate to the scale here. Now, if I consider that the shorter wavelengths in gamma rays and X-rays is higher energy, so in fact, let's label this. So this end of the electromagnetic spectrum is high energy, where my gamma rays and X-rays are. My low energy range is going to be out here in the radio waves. So if I look at these regions of the electromagnetic spectrum, I'm going from high to low, and I'd like you to memorize the order. High energy is going to be gamma rays. Then as we drop in energy, we're going to have X-rays, ultraviolet, visible, IR, microwave, and radio waves. If I want to consider wavelength, though, wavelength is inversely proportional to my frequency. In fact, I can write an equation for energy. My energy can be equal to a constant called Planck's constant times frequency. Okay, so you do not need to memorize Planck's constant. I'll give that to you here in a minute, but I give it to you on a test. But energy is directly related to frequency. So as frequency is greater, 10 to the 20th hertz here, we have higher energy. As frequency is less, 10 to the 4th hertz, we have lower energy. If I want to recognize that I can relate energy to wavelength, I can use the equation I have here, but I can just rearrange to solve for frequency. So frequency would be equal to my speed of light divided by wavelength. If I recognize that, I can insert this version of our equation relating wavelength, frequency, and the speed of the electromagnetic radiation. We can insert that into frequency for our energy equation. And so energy is going to be equal to the constant, Planck's constant. Like I said, I would give that to you on a test. Don't worry about it right now. But it's going to be Planck's constant times the speed of light, which I told you to memorize is 3.00 times 10 to the 8th meters per second to 3 significant figures, divided by wavelength. Now, what I want you to notice that's important here with looking at these two equations, oops, that should be a lambda down there. If I'm looking at these two equations, energy is directly proportional to frequency, but it's inversely proportional to wavelength. So that makes sense. At shorter wavelengths, I have higher energy. 10 to the negative third nanometers is the highest energy in gamma rays on this list. If I look at 10 to the 13th, so longer wavelengths, lower energy. So recognize that inverse relationship between energy and wavelength, and the direct relationship between frequency and energy of the electromagnetic radiation. I might ask you on a test to list frequency from high to low frequency, or wavelength from high to low wavelength, and realize they would be reversed for the orders of the electromagnetic spectrum. Or I might ask you to list the electromagnetic spectrum from high to low energy. So make sure that you could do that for an exam. Now that while we're looking at this, I want you to note that there's a very short region of the electromagnetic spectrum that we can see with our naked eyes. We have to use other types of detectors to see the other regions of the electromagnetic spectrum. But if we look at the visible range is roughly from 700 nanometers to 400 nanometers. You'll notice that the higher energy range of the electromagnetic spectrum is going to be out here in the violets and indigos. My lower energy with the longer wavelength is going to be out here in the reds. So infrared is actually lower in energy than visible light. And all warm objects are radiating the electromagnetic spectrum in the infrared. So we can go ahead and see the body heat of people if we can design detectors to see in the infrared, and certain insects can see out there in the infrared a little bit to help them find warm bodies. If we look out here beyond the violet, we can see we have ultraviolets higher in energy as we get to shorter and shorter wavelengths. So that gives us a rough idea here. But if we're working problems and we see somewhere between roughly 7 to 400 nanometers, we know we're in the visible range. We can see that type of wavelength with our naked eyes. Outside of that range, we're going to have instrumentation to help us out. Okay, so let's use a few of our calculations here to solve for the relationship between wavelength and frequency. So I have for a reference here our electromagnetic spectrum. Let's consider that you might go to a dentist's office. If you go to a dentist's office, there's a number of different types of electromagnetic radiation you might be observing in different ways. The dental hygienist might take an X-ray of your teeth, and let's say the X-ray you're told has a wavelength of 1 angstrom. Okay, and then while you're also there, you're listening to a radio station with a wavelength of 325 centimeters. And you're looking out the window, and the blue sky you see has a wavelength of 473 nanometers. With that information, let's convert these different wavelengths into frequencies and see if they relate to our electromagnetic spectrum where we would expect these different regions to be. Okay, now the first thing we have to recognize is that all of this electromagnetic radiation is going to be traveling in a vacuum at the speed of light of 3.00 times 10 to the 8th meters per second. Okay, let's find its frequency in hertz, which is going to be cycles per second, so it's going to be inverse seconds here that we're looking at. Okay, so as I set this equation, first of all, I need to relate my wavelengths to meters. Here's the reason why. When I'm thinking about the speed of light, right, my speed of light I should memorize as a constant, or my speed of electromagnetic radiation is 3.00 times 10 to the 8th meters per second. Okay, so since this is in meters per second, I want to convert all of my wavelengths to meters. So I need to convert the angstroms to meters. So that's the very first thing I'm going to do. So I need to recognize that 1 angstrom is 1 times 10 to the negative 10th meters. It's a tenth of a nanometer. Remember, nanometers are 1 times 10 to the negative 9th meters. So an angstrom is a tenth of a nanometer. When we were first looking at the metric system unit conversions, I said this is one we would likely use in the course, and you should learn this one as well. Okay, so if you haven't learned it before, make sure you know that 1 angstrom is 1 times 10 to the negative 10th meter. So my angstroms will cancel, and I find that if this is 1 angstrom for the wavelength, is 1 times 10 to the negative 10th meters for the wavelength in meters. Now I'm using my equation that the speed of the electromagnetic radiation c is equal to wavelength. I'm using the Greek letter lambda for wavelength times frequency. I'm using the Greek letter nu for frequency. What I'm going to do is solve for the unknown variable. I'd like you to solve for the frequency here, the Greek letter nu. Okay, so I come up with the following equation. Nu is equal to the speed of light divided by wavelength. I just went ahead and divided by both sides by the Greek letter lambda to solve for my algebraic variable. So I put in my speed of light, 3.00 times 10 to the 8th meters per second. My wavelength is 1.00 times 10 to the negative 10th meters, which we solve for up here. Okay. Now, if I had forgotten to convert this to meters, as long as I write my units down, I could see that angstroms would canceled with meters. It would have reminded me to do this first step. It's when you don't write your units, you forget to have those reminders that can help you solve for these problems. So we predict that the frequencies for the X-rays that they used to take the X-ray of your teeth was 3.00 times 10 to the 10 to the 18th hertz. Let's see if that's reasonable for X-rays. Let's go ahead and look at our electromagnetic spectrum. Let's see, 10 to the 18th hertz. Yeah, that's right here. That would be reasonable for a frequency for X-rays. So that makes complete sense. Okay, so we can double check our work if we know these regions generally of the electromagnetic spectrum, or if we look them up in our notes or textbook while we're doing homework problems. Let's solve for a couple of other frequencies and relate them to the electromagnetic spectrum. We're also listening to this radio station. So we had a wavelength of 325 centimeters for the wavelength for the radio station. I want to convert that wavelength from centimeters to meters again, so it plays nicely with our electromagnetic radiation speed of the electromagnetic radiation of vacuum, constant c. So my wavelength here is 325 centimeters. I need to recognize that there's 100 centimeters in 1 meter. So every 1 centimeter is 100th of a meter, 1 times 10 to the negative 2 meters. Okay, so my centimeters will cancel, and I find that I have 3.25 meters that I predicted for the wavelength for the radio station. That's a much longer wavelength than we were seeing for the X-rays, wasn't it? So I went ahead again and solved for frequency in my equation. Frequency is equal to the speed of light divided by wavelength. So I have the speed of electromagnetic radiation of any type, including light, is 3.00 times 10 to the 8th meters per second, divided by the wavelength as 3.25 meters. And so my meters will cancel, and I have inverse seconds and cycles per second. Those wavelength cycles, those inverse seconds, is my hertz. So that would be 9.23 times 10 to the 7th hertz. Let's see if that's reasonable for radio waves. And so if I take to the 7th, that's going to be right here. So that's here in my radio waves region. So that makes sense. So you could be listening to that radio station with that wavelength. The other thing we were looking at was the blue sky out the window, where we were trying to relax while they were doing all of our dental work. So the blue sky, we were told, had a wavelength, Greek letter lambda for wavelength, of 473 nanometers. So I need to convert from nanometers to meters. So hopefully you remember that nanometers are 1 times 10 to the negative 9th. Meters is 1 nanometer. So I take 473 times 1 times 10 to the negative 9th meters for every 1 nanometer. So that tells me that I have 4.73 times 10 to the negative 7th meters here. Now my frequency of the electromagnetic radiation from the blue sky will be equal to my speed of light, 3.00 times 10 to the 8th meters per second, divided by 4.73 times 10 to the negative 7th meters. That gives me a hertz, or frequency, of 6.73 times 10 to the 14th hertz. Let's see if that would be reasonable for visible light. So let's take a look at that. So if we look at it, here's 10 to the 14th. We're a little above that because we're at 6.34. So we have 6.34 times 10 to the 14th hertz here for the visible range of my spectrum. Okay. Now let's consider we have a sodium vapor lamp. If we have a sodium vapor lamp with a wavelength of 589 nanometers, and if I want to solve for the energy of a single photon of that radiation in joules, let's see how we would do it. The equation that we have for energy, as I showed you before, my energy is going to be equal to a constant, Planck's constant, which I would give you on a test. You do not need to memorize Planck's constant, but you should memorize the energy is equal to Planck's constant times the frequency of the electromagnetic radiation. We know that the speed of electromagnetic radiation, c, 3.00 times 10 to the 8th meters per second, is equal to wavelength, Greek letter lambda, times frequency, Greek letter nu. Okay, if I would like to relate wavelength, and I know here I want to relate wavelength to energy because we were given wavelength, not frequency. So I have two options here. I could either go ahead and plug in my wavelength to this equation and plug in my speed of electromagnetic radiation and solve for frequency, and then put the frequency in this equation, or I could algebraically substitute for frequency by using the two equations. So let's say we want to substitute frequency to relate to wavelength. So my wavelength, if I divide both sides of this equation by frequency, is equal to the speed of light divided by frequency. And if I plug that into my equation here, I can generate the following equation. Okay, Planck's constant times the speed of light over my wavelength, lambda. Okay. So if we have just one particle of light, one photon of light, okay, we can treat the a value that's sometimes shown as n in this equation before Planck's constant as a 1. So that's what we're going to assume here. We just have one particle of light, so I just have a 1 in there. And if I don't show you n, that's what you can assume most of the time. Now I need to convert my wavelength to meters so that we can use the speed of light constant in meters per second. So I have 5.89 nanometers. I know there's 1 times 10 to the negative 9th meters per every 1 nanometer, so that's going to be equal to 5.89 times 10 to the negative 7th meters. Okay, that's how many meters I have that I'm dealing with in this case. Now I can go ahead and solve for my energy by plugging the wavelength in meters in for the Greek letter lambda here. Okay. So I'm going to go ahead and solve for energy. My energy is going to be Planck's constant. Now I'm giving you Planck's constant here as 6.63 times 10 to the negative 34th joules times seconds. So we're going to solve for energy in joules here. Now if I multiply by my speed of light, my speed of my electromagnetic radiation, I have 3.00 times 10 to the 8th meters per second. My seconds will cancel, you see here. And if I divide by my wavelength here, Greek letter lambda, I'm dividing by 5.89 times 10 to the negative 7th meters. You'll notice that your meters will cancel, and you're going to end up with joules for the energy of this electromagnetic radiation as being 3.38 times 10 to the negative 19th joules for every particle of electromagnetic radiation, which is going to be called a photon. For every one photon. Okay, so let's say we have a cook who's using a microwave to heat a meal, and the wavelength of radiation for this microwave is 1.20 centimeters. Let's find out what the energy is in this case for a single photon, a single part of light, for this microwave radiation. Since I'm given wavelength, I can use this following equation for my energy. Remember, if you were just given frequency, well, that's quite simple because your energy for a photon of electromagnetic radiation, if I have frequency, is merely Planck's constant times my frequency in hertz. Okay, so it's this equation I would use. So I can decide I can use this equation if I have wavelength, this equation if I have frequency, and I would like you to have these equations memorized or be able to generate them on a test. Okay, so I go ahead and plug in my wavelength here. of 1.20 centimeters. I'm going to convert it from centimeters to meters. I know there's 100 centimeters for every 1 meter, so that's going to be 0.012 meters. You could also have written this as 1/100th of a meter over 1 centimeter. You would have had the same conversion factor and gotten the same value if you'd written it that way. Now my energy again is Planck's constant. On a test I would always give you Planck's constant, so you don't need to worry about memorizing it, but you need to be able to recognize that you use it in this scenario. Okay, I multiplied by the speed of light. I did ask you to memorize the speed of light, or the speed of electromagnetic radiation, as being 3.00 times 10 to the 8th meters per second. I'm going to divide by my wavelength here, which is going to be my lambda. When I divide by my wavelength, I'm going to see that my meters cancel. My units for my Planck's constant h is going to be joules times seconds, so my seconds will cancel, and I'll have units of joules, so I have 1.66 times 10 to the negative 23rd joules. Okay, so let's compare the different wavelengths and the energy that we're looking at. So for visible light, we have 3.38 times 10 to the negative 19 joules for every photon. For microwave radiation, we have 1.66 times 10 to the negative 23 joules. So we'll notice that microwave radiation for every photon has less energy than that of visible light. Let's see if that makes sense. If we look at visible light on our spectrum, we see that visible is going to be, since the left-hand side is high energy, and the right-hand side is low energy. We can see that the visible light is higher in energy than the microwave radiation based on our electromagnetic spectrum. Okay. The reason we use microwaves in order to cook our food in our kitchens is that it's very effective at causing motion in certain molecules, some types of proteins, but water quite a bit. So water molecules will absorb microwave radiation quite effectively. It will cause that those water molecules to rotate and give them kinetic energy, and they'll end up striking other molecules and heat other molecules in your food. And so if you bombard it with enough microwave radiation, even though it's lower energy per photon, you can definitely heat up food just fine. But there's solar cookers too. You can use visible light to cook food as well. It's just not always as convenient because you have to rely on having a good source of solar energy for the visible range, and so in this case the microwave radiation will work quite well. And usually with those solar cookers you're also getting some infrared and other regions of the electromagnetic spectrum contributing as well. But it's just something to realize. We can predict the range of energies for photons using the electromagnetic spectrum as a reference. Okay, so I'm going to stop there today. Our next video we'll be looking at the Bohr model of the hydrogen atom, and then we'll be looking at using what's called the Rydberg equation to calculate my different wavelengths. Okay, have a great day, everybody.